Hello, hello. Okay, hello everyone. Welcome to the Swift as C++ successor in FDB, FoundationDB talk. My name is Konrad. I work at Apple on the Swift team. I mostly focus on language and runtime for concurrency and distributed systems, but also server-side libraries in general. So this talk is a bit of a case study, how we adopted Swift in a large existing code base that's predominantly C++. And I'll introduce you to some Swift features along the way. So for those who don't know, Swift is a natively compiled general-purpose language. It's the language of choice on Apple platforms, but it's equally well supported on other platforms, for example, Linux, and there's a vibrant server-side ecosystem, people building and deploying services in Swift. In general, we have a very strong focus on safety, both memory safety and concurrency safety, and I'll zoom into this a bit more. At the same time, though, Swift doesn't sacrifice ergonomics to achieve this safety. We strive to be a great first programming language. You can imagine you've never programmed before, you want to pick up some language, write an app for your phone. It can't overwhelm beginners with a ton of difficult stuff, right? At the same time, we have use cases that are really soft real-time systems, system libraries, or even the kernel that also want to be using Swift. So we really have to scale from the simplest beginnings to the most advanced use cases in the same language. And to do that, Swift is really optimized for both performance and predictability. You can predict where and how things are going to be allocated. There's no GC with unpredictable behaviors, and the overhead of the runtime is generally very low. And it's evolved using an open development process, so you can propose things to the language, just as a community member. So I should probably define what I mean when we say successor language. So successor language, generally we think it's whenever you're about to use C or C++, you should think again and use Swift. So predecessor languages in our mind are C and C++. The predominant reason to build a successor language is safety. So we want to entirely eliminate an entire class of bugs, predominantly memory and concurrency safety ones, because they can manifest as security issues. So this is something we really want to eliminate as much as possible. We can't really just patch up C++ because, well, it's going to be patched up C++, and the core of C++, the way it manages memory and all these easy to make mistakes would be still there. So we want a clean cut between safe by default languages, Swift, and the predecessor languages. And Swift has a great story for interoperating with C. It was a key for its success on Apple platforms, and we've really focused on that. And we've brought the same experience to the C++ interoperability in this year's release. And to finally introduce our last actor in this show, FoundationDB. So FoundationDB is an open source key value data store. It has distributed transactions over multiple keys, and it is it's open source and was acquired by Apple a few years ago. FoundationDB is in the critical path every time you're using iCloud for signing in, accessing your email, contacts. So it's a massively critical service for Apple. It's also used by other companies like Snowflake and others. A crucial piece of what makes FDB so interesting and successful is its simulation testing runtime. So FDB is able to run millions and millions of tests with, injecting failures, reordering messages, injecting delays, kind of a chaos testing environment. But as it does so and finds an issue, we're able to reproduce the exact execution of the entire program to reproduce the same issue. So you can reproduce how did this crazy edge case happen, and you can have it reproduce every single time and find the issue. So really amazing for finding edge cases. This is made possible by a custom language called Flow. Flow is a C++ dialect and was developed along with FDB, so it's more than 10 years old by now. It's a C++ dialect in the sense that it adds a few keywords and syntax to C++, but actually it's not really a full-blown language, but a source generator that generates C++ from those extra pieces. it's really what kind of enabled this simulation testing runtime, because it has all the hooks where we can inject all of these reorderings. So it's probably fair to say that FoundationDB is really made possible by this tight integration of the language, the concurrency runtime, and this testing facility. So it's really something really enabled by Flow. At the same time, it's been 10 years since Flow was first introduced, and FDB are looking to kind of modernize and improve from the things that are kind of starting to show its age. So the FDB team went through and thought about, okay, what do we need to improve for another 10 years of successful database, right? And the first and predominant issue here is the memory-unsafety of C++. We really want to have an environment where we can be more reliant on the language providing us help with development and not fight the language and trying to prevent all these bugs. The other issues are that the Flow language is kind of a side product, and it being a source generator is kind of showing its limits. The amount of nice diagnostics and features you can do as just a source text-based source generator are fairly limited. And the runtime is limited to being single-threaded. You cannot go multi-threaded with Flow, it just wouldn't work. So we also should do something about that, because modern hardware, things have changed in the last 10 years. We really want to use multi-core, even though initially it was a good idea to be single-threaded. And the usual of debugging C++ programs and debugging concurrent C++ programs, it's a hindrance on adoption, hiring, and debugging, just loss of developer productivity. So that's things the team would like to address. And they came to us, the Swift team, saying, well, we heard Swift has actors and has all these nice things, maybe we can replace Flow. But as we look at these requirements, it turns out that, well, we're not actually trying to replace Flow here, because in order to get memory safety, concurrency safety, it wouldn't really matter if you change the source generator. You still have C++, and it still has all these issues. So we're actually looking at an exercise of replacing C++. And that is one of the things Swift is good at. And it's another great case to showcase our C++ interop. So that's what we did. There's a PR here that is merged in the upstream FoundationDB repository, and we started an incremental adoption of Swift side by side the existing C++ codebase. Okay, so to reform these requirements that were stated before into a few steps that we can walk through, we'll have to start with actually being able to compile Swift together with the C++ codebase. As many C++ projects, FDB is built using CMake. A typical CMake file just declares a bunch of modules, and thankfully, Swift will be able to just consume Clang modules. Our goal here is to be able to plop in Swift files right next to the C++ files, because this way we're able to see, okay, for example, master server Swift. Oh, so we started migrating this file, this actor, into Swift. You could totally have a totally separate module where you put all of the Swift files, but that's really up to how you organize your CMake project. We thought this is more interesting because visually you have direct feedback. Oh, I can already use some Swift here. So building Swift. Of course, we have our own package manager that can build and download dependencies, run tests, as you would expect, but we can't be using that here because we want to incrementally add Swift to this existing build with as little fluff and break everything along the way as possible, right? So instead what we'll do is we'll use CMake to build Swift. And the good news is that CMake actually has built-in support for Swift, and all you need to do is in your project say language Swift, and you can start adding Swift files to your CMake build. Worth noting is that some libraries actually are even built using CMake themselves, so both using the Swift package manager and CMake. So if you wanted to pull in some of the popular like better collections that are a bit more than the standard library offers, atomics libraries, or many others, you can actually do this using CMake as well. So let's include some Swift files in our FDB build. To do that, we add a new library. That's how you declare a target in CMake. We call it FDB server _ Swift to mirror the FDB server target. And you just start adding Swift files there. We make this, all of these Swift modules, a dependency of the FDB server, the C++ target, and that's really all we need to do. And then we can open up our Swift file and write some Swift that actually uses C++ types. So when you see these import flow, import FDB client, those are actually importing C++ targets. And all the blue types here, so master data, the request here, all the function calls here, are actually coming directly from C++. So as this is the first time we're calling C++ in this talk, let me explain how this actually works. So, as I just said, you can import existing Clang modules, and Clang modules are basically just a collection of C++ header files. The Swift compiler is able to understand header files, and this way we basically know, oh, there's a get server knobs function. But it gets much more interesting than that, because as the Swift compiler is importing this module, it can actually inline function bodies, because both Clang, so the C++ compiler, and Swift are operating on LLVM, and what actually is emitted during compilation is LLVM's intermediate representation. So what Swift-C does is ask Clang that, hey, can you please emit this inline function body into my compilation unit, and it is the actual LLVM intermediate representation being emitted directly into the Swift binary or library. And because the LLVM optimizer also works on this layer of abstraction, so the LLVM's IR, it can even optimize across the languages. For example, if you had a few calls, calling here, there was some null checks maybe, it could automatically realize, even though there's a language barrier here, LLVM doesn't really care. It can optimize as if there wasn't a barrier at all. So in that sense, it's a bit unfair to call it just an interop feature, because it's much more. It's not FFI, there's no wrappers, there's no bindings you have to generate. You're literally calling the C++ code directly from Swift. Okay, let's look at the other way. So let's say you have some C++ code and you want to call Swift. We'll have some Swift function implemented here that we want to call. The way you do that is you include a Swift generated header. So as Swift compiles in the interop mode, it generates a header that C++ can understand for all the public declarations. So we just import that header, and we can call the Swift function. As far as C++ is concerned, this is normal C++ code. There's nothing magical about it, so everything works as you would expect. We can pass C++ pointers here, and it will end up just calling the Swift function. Yep. So here we're returning a future that's also a C++ type, and then we use flows await on it. Okay, let's talk a little bit more about the language model, about the object model of both of these languages and how they can interop. First, let me introduce Swift a little bit. So Swift leans heavily on value types. So value types, you can think of them as behaving the same as a primitive. So for example, here we have a wrapper struct. It has a value inside, and we're also modeling mutation explicitly in Swift. So you can see there's a let declaration and then a var copy. So semantically, there will be a copy performed when we do this var copy assignment. And as you can see, trying to mutate a let assignment is not allowed by the compiler, but of course you can mutate the copy and not affect the original value. That's what we mean by value semantics. This is great for all kinds of reasons, just local understanding of your code, not accidentally mutating something you didn't intend to. And it's also great for concurrency, because if everybody has their own copy, there's no shared mutable state, everybody's happy. We do a bit more than that, though, and I would like to introduce you to copy on write value types. For example, collections in Swift, such as arrays, dictionaries, and sets, are also value types. And you might be thinking, well, isn't that a horrible idea, because we would have to be copying the entire array all the time when passing it around. So instead, of course we don't do that, that would be silly. Instead what we do is when the collection is uniquely referenced, we can mutate them in place. And as they are passed around, here we have two functions called pass and mutate please. As you pass these items array around, it still isn't copied. It is only copied once you try to once you attempt to mutate, right? So at the bottommost function here, we have var c items that still didn't copy, although semantically you can imagine as if it did. But as you do see append, that is where the copy is made. And from this point on, you have your unique storage, and further mutations are made in place. It's a really powerful semantic that we use in a lot of types in Swift. And of course, we have reference types. Reference types use reference counting, atomic reference counting in Swift. So you get predictable characteristics on that. And you cannot really have a null pointer per se. If you wanted to express nullability, we force you into using optional types and actually unwrapping safely. Okay, let's compare it to C++ and see how things can import across languages. So a C++ struct or class imports as a value type by default. And usually that's the right thing to do. So it would just use the C++ type's copy constructor. And if the copy constructor is deleted, well, clearly we can't be copying it, so we will not import that type. On the other hand, a C++ reference type is a bit more, importing a C++ reference type is a bit more involved. And this is primarily because it's not really clear from looking at the declaration side of a type, like here, this global counter. Is it a reference type? C++ doesn't really well specify that. And it's more about how you pass things around and how you allocate them, where you can notice, oh, it's intended to be used as a reference, right? So you pass it around as a pointer, a shared pointer, but in the same code base, you totally could have a function accepting a value of that struct. It's technically not incorrect, but the compiler wouldn't really know what to do with this. So we need a little bit of input from the developer, and the way you do this is including the Swift bridging header, which includes a bunch of macro annotations that you can put on your types, and then declare, okay, so the global counter, I know this is something that we allocate once, it's a global thing, a global singleton, so just assume it's a reference, and don't even perform any ref counting on it. I know this is going to live forever. So this way, the way this is imported into Swift, it's going to be treated as a reference. Of course, that's the easy path. That's the simplest case because we didn't actually ref count it. More interestingly, we would like to import types and actually ref count foreign types declared in C++, like the master data here from the FDB codebase. So as I'm done using it, I want it to be deallocated, released, right? If we look at the declaration of it in C++, we can see that, okay, it's non-copyable and it's reference counted. Okay, what is reference counted? Reference counted is a custom implementation of intrusive reference counting that FDB has defined. And the reason they do it is because, well, sometimes it's thread unsafe because we know we are a single-threaded runtime. We don't have to use atomics here, so they can rely on using that. Although there's an atomic version as well. Now, this is just an example of a typical thing that happens in C++ code bases, which is a lot of weird custom stuff to manage memory. And every code base will have its own slightly different approach to this. And the important thing with the interop feature for Swift is so we can support all kinds of these patterns. So what we can do, again, is to bring in the Swift bridging header and declare, okay, this is going to be a shared reference, and whenever you want to retain or release an instance of this class, struct, call these functions. This informs the Swift compiler when using this type in Swift to call these native C++ functions to retain and release this object. So we're automatically going to manage the lifetime for you here, using whatever reference counting scheme you have in C++. That is not all, though, and we should do a bit better than that, really. Because, okay, we can call methods, we can refer to types, but if the usage of those foreign types doesn't feel natural, it will be kind of weird, right? And people will be like, maybe I'll stick to C++. But our goal is to eventually replace more and more code with Swift, because we want the safety properties. So not only does it have to kind of just work, it has to feel great, so people are incentivized to use more Swift than C++, right? And we're not used to it, so the easier we can make it, the better. Okay, so there's 3 pieces to that I want to highlight. Memory safety and object lifetime, we just talked about. As long as you annotate your types correctly, this will just work. Next, worth highlighting is collections, or C++ containers, STD containers, because by the end of the day, we use a lot of collections in our code bases every single day. And they usually have some kind of niceties in the languages we use as well, right? So thankfully, Swift is able to import collections/containers, and you're able to use an STD vector in a Swift for loop, or use for each or filter, methods you would expect from Swift to be able to call on these collections, right? At the same time, methods that are just std vector methods are also available, so you can use whatever feels right. And the same is true for dictionary types like map, and here the interesting bit is that yes, we're using a subscript to get something out of this map. However, this is going to return a Swift optional. So again, you're not going to have to deal with safety of those accesses. It's going to force you into the you have to check, right? And perhaps most interestingly, and the use case I want to dive deep into, is how we want to interact with concurrency declared on the C++ side. And the tricky thing here is that C++ doesn't really have one way to do concurrency. You might be using various libraries. Maybe some are using futures. Maybe you wrote your own things. And this is the case in FDB, where the flow language and library come with their own definitions of futures and promises. And this is the primary way you do async in Flow. So of course, as we call these functions declared in C++ using the Flow library, Swift wouldn't really know how to treat this and magically turn this into an async await call. But this is what we idiomatically would like to do. In Swift, the idiomatic way to do such a call would be to await an asynchronous function, right? But we can't write such a function in C++. So how can we do that? Before we jump to the solution, let me introduce you to two Swift features. One is extensions. So extensions allow you to add methods to existing types, even if they're declared in other modules. So you can just write an extension on the notified version value, and we can implement our at least asynchronous function in Swift. That's one way to do it. We can do a bit better than that, though, and we can declare a protocol that is similar to interfaces in other languages, in the sense that it's going to declare, okay, things conforming to this protocol will have to provide implementations of an at least async function. So we can declare this. So we have an API contract, and then we can post hoc conform an existing type to this protocol. So we take this C++ notified version value, we conform it to the notified operations. Okay, the compiler will now demand from us that we provide an implementation for this at least async function. But instead of providing it for this concrete type, we can provide it for all kinds of notified operations, right? So this way we are able to implement this bridging code in one place, and then every conforming type is able to get the implementation for free. Let's have a look at how we would implement this, this at least function. So to implement it, basically we can direct to the C++ implementation, get the future out of it, and then await dot value on it. But wait. Where does that dot value function come from, right? I didn't actually define it. And is this going to be one of those where, okay, for every single type we have to go deeper and deeper and keep adding functions one by one? Thankfully, no. And I want to show you specifically on the future type what we can do better here. So the future type, as you might expect, is a class template, because there's various futures, future of int, future of void. And while we cannot directly extend it in Swift today, we can ask the compiler that, well, while you're importing this type, or instantiations of this template, I should say, please conform it to this protocol. Then we can express just enough in the Swift type system to have enough to be able to implement a generic value implementation, and make sure that the Swift requirements match up with the C++ types implementations. So yes, you do have to spell out the spellings of those methods in Swift, but thankfully you can always look up how Swift sees a C++ interface by opening up the imported module file. So you can easily find that out. So now we can write an extension on our flow future operations and provide this value implementation. The implementation itself isn't too exciting. It's a lot of boilerplate, but the point being, and it doesn't really use anything we didn't discuss, so I'm going to skip it. You can find the implementation, though, if you want, in the repo. The point being, though, is for every instantiation now, as we're importing those types into Swift, the compiler will also conform it to this protocol because this protocol has this default implementation of a value, we can just call it on whatever future we might be using in our code base. So we're able to write this code, basically. And there's kind of layers to how much effort we want to spend. For the future type, we went all the way in with this protocol conformance and default implementation because futures are used everywhere in the code base. But at the same time, we could have still just said when at least and then do the dot value, but we can also provide nicer APIs that look more idiomatic when it's worth doing so. And I think it is worth doing so because the more nice it feels to write code in the Successor language, the more interested you are in using it, right? So small things like that pay up in the grand scheme of things. And the best thing, of course, is that the nasty implementation is hidden away in one place. You don't have to, every single time you use a future, do a bunch of workarounds. So that's really important. Next up, let's talk about concurrency. So concurrency has its own set of challenges. And again, our focus will be on safety and ergonomics. We need to improve both of those and improve both upon the C++ unsafety, and we have to integrate with this existing FDB runtime that I told you about for simulation testing. So how can we do that? Before we jump in, let me introduce a typical kind of race or question that might arise in C++ code. The illustrating code is in this flow language, but conceptually it's just two actors which may execute concurrently, the force recovery actor and the track recovery actor, and they're both referring to this shared reference to a mutable state. Now, I named it here pretty obviously that, ooh, mutable state, and this might be not a good idea, but in a real code base, it might be hard to spot, is this a correct access or not? And if you were to ask the question, well, is this safe to share this reference between these actors? The answer would kind of depend on both who you're asking, if the person is experienced or not with this specific code base, or if they've had their coffee or not, right? Maybe they're too sleepy. Oh, yeah, it's fine, whatever. So the problem here is that it's up to the developer to double check every single line of code and verify, this probably is correct, right? In the FDB case, there's kind of a weird answer here that on the low-level concurrency level, because the runtime is single-threaded, sure, this won't cause like memory corruption or races in that sense. However, it still might not be intentional that this mutable shared state was actually shared between the actors, and you can't really know, right? You would have to go in and start some detective work if this was intentional or not. So this is a problem because FDB would like to use more concurrency in the system, but we don't really have a way to gain more confidence in this unchecked word. Yeah, we introduced actors, but because it's still C++, we're still wrangling with the same old issues of non-checked concurrency, basically. So here's how Swift fits into the picture. So Swift's approach is to be safe by default. We mean that about both memory and concurrency. So we achieve that for concurrency with compile time checking. So actor isolation and sendable checking both come together and basically make it impossible to write incorrect code. Sometimes when we're unable to confirm if something is safe or not at compile time, which is actually very rarely, we would insert runtime checks, but that's as a fallback. I mostly mention that to highlight that we will value safety more than anything. And yes, there's going to be opt-outs, but the kind of default mode is switched from the predecessor languages, where the default mode is, oh, nothing is safe, good luck. For us, safe is the default. So Swift actors. Actors have been around for a long time and implemented in many languages and libraries. And as you've seen here, FDB also implemented them more than 10 years ago as a library solution. Now the problem with library solutions to actors is that you're still on the host language, and the host language will have concurrency holes in it. As another example, my previous life before the Swift team was working on Akka, the kind of actors on the JVM, and it's also a library solution. And while you stay in the correct patterns to use Akka actors, you're safe. But the moment you touch a Scala future type inside an actor, oh, suddenly you broke concurrency, right? Because we can't prevent you from doing unsafe things as a library. But as a language, as Swift is, we can. So let me introduce you to that. To introduce an actor in Swift is very easy. Instead of having a reference type like a class, you can make it into an actor. Now the compiler will start emitting warnings and errors in all kinds of places because now you're probably violating actor access rules, actor isolation. For example, here we have a counter and we're hitting the counter to increment its count, and the compiler says, well, but this is async because interacting with actors, the actor might be already doing something, so we may have to suspend you. So you have to acknowledge that by writing a wait, because this is a potential suspension point. We call those potential suspension points because there are actually cases in which we don't have to suspend and can call directly, but that's dependent on a few executor details, so you can treat it as an optimization. And if we were to model the previous example here using Swift actors, this is what it would look like. So we have a recovery actor, we have a recovery tracker, and I'm trying to escape the self state. And the compiler will tell you that, hey, you're trying to send a non-sendable type mutable state into an actor isolated domain. You probably introduced a data race here. Today, this is a warning. We will be upgrading all of these into hard errors in the upcoming major release. And I would like to highlight that, well, the previous example was kind of easy. You just escaped a variable in the call, but this is very deeply integrated into the language, including escape analysis, enclosures. And for example, if you had a listener type that has a call me later, that takes a closure, it depends how this closure is being used if this code is correct or not. If you're guaranteed to synchronously invoke this closure, then this code is correct. But if it's actually going to escape this closure and use it somewhere else to then later call you on a different actor or thread, this is unsafe. So the compiler can holistically analyze, and by annotating code correctly, you're able to get help from the compiler. If you actually would want to share the state, the recommended way would be really to make it a struct, because that's easy to, thanks to value semantics, you can very easily then send it around. Or you can use actor isolation and make other code run on the same actor. And then by using the actor semantics of only one thing runs concurrently at a time on an actor, you would also be safe and could still be using the mutable state. An interesting thing here is that you can actually declare new methods on actors using extensions. And this is interesting because there's a duality between access control and kind of concurrency control. Because what we just did here is this entire function will be running on the actor, and we can, for example, flip a few things on the actor's internal state without hopping off it. So we get atomicity as we do these updates. That's something not many other actor runtimes can do. To me, that's very exciting. So to compare this again to the existing state of FoundationDB, FoundationDB's actors are a bit of a pattern, really. So you see there's these future returning functions, and they have to pass around the self object because it's kind of representing the this of the actor. If we were to turn this into Swift, firstly, okay, it looks a bit more like normal code we're used to reading, but primarily we already got the gain of actor isolation checking. So all this stuff about, oh, you can't escape values, you have to go async to access it, we already got a benefit here. Now we can implement a concrete function, so I can show you how to use actors from C++. So here we have our master data actor, and we're implementing the getVersion function. And to export this actor to C++, which is down below, trying to use it, all we have to do is to make the actor public. For C++, this looks and behaves just like a reference type, but it will not be able to call the async function because C++ doesn't really have that notion of async functions. So yes, we would have to write a little bit of boilerplate to bridge our async code into the world of flows, futures, and promises. So that's unfortunate. So we would have to write this piece of boilerplate for every single function we're exposing to flow. It's not so great, but thankfully, again, Swift has us covered because we can use a macro for this. Swift macros new in this release are syntactic macros. They work on the AST, and unlike C++ macros, where you can pretty much generate, well, not random, but pretty free-form things, this is based on AST abstractions that you can very easily manipulate. And so we can do that in a macro. Finally, I said that FDB has this concurrency testing runtime. How it works in practice is the source generator splits up this function into various classes with state machines inside them that represent jobs that are submitted to an event loop. That event loop can be either the simulation testing one or the production one. And as long as we would be able to submit jobs into this existing runtime, it would basically work, because it's just a runtime that, I'm going to delay this job a little bit, or I'm going to reorder these jobs a little bit. So Swift is actually quite similar to that, because we have tasks and jobs, which we have a hook for that we have overridden to then, instead of submitting jobs into Swift's concurrency pool, can basically wrap the existing Swift tasks and jobs into a type that already exists in the FDB code base, and whenever the FDB event loop tries to run them, well, we're going to call Swift run on the job instead. So the integration here was fairly easy, surprisingly. And last but not least, to continue the thread on developer experience, of course, all of this Swift and C++ interop works great in Xcode, but we know that people use various IDEs, so we have a language server implementation for Swift, and you can use whatever IDE you like. You can use VS Code, Vim, Emacs, whatever has a LSP client. To showcase this in action a little bit, here's a screenshot of VS Code with the SSWG, so server-side workgroup, server-side Swift workgroup maintained plugin, and that plugin uses this LSP server to provide a nice developer experience. And you can see it both auto-completes Swift types and types coming from C++ in a Swift file that can autocomplete and everything. And the last thing I want to cover is developer experience of debugging crashes. So here's how a crash looks like today in FoundationDB, and typical for a C++ program, it would crash and give you a way to, well, if you still have the debug binary, you can use this command to get a backtrace. So you take this command, you run it if you're lucky enough to still have a binary lying around, and then you have to play with finding your code, because it's all source generated, and actually mapping your code to the backtrace is not going to be trivial, but eventually you will find the code, right? So that's a complaint about the source generation aspect. But the real issue here isn't about the source generation, but about futures and promises themselves. If you have a chain of futures and promises, so here we have two promises, and then we take one, succeeded. As this first one succeeds, we succeed the second one, so we kind of cascade the value up a chain of futures, up a chain of promises, and then in the second one we crash if we got some bad value. The way a backtrace for such a thing would look like, regardless of futures implementation really, is something like this. A lot of library code, and yes, finally you will get your line with the crash, but you will never get the line you're actually looking for, which is, where did this bad value come from, right? So in future implementations, you don't really get the entire context. You only get the, oh, this is the crash site. So that's pretty frustrating. And let's compare that to what we can do in Swift. So in this example, I have a task that then calls an async function, calls another async function called check, and we're even calling into some C code here that will eventually crash. This is how the backtrace would look like for this. So instead of having to guess around where the code was actually crashing, I hope this is large enough. It should be. You get a full backtrace spanning multiple languages. We're going to include the C or C++ code where you actually crashed, and then continue through the asynchronous suspension points. So, sorry, I should mention, we're going to demangle the C++ symbols as well, if you have them here. Include source location, And the backtrace is logical, so we're actually going to follow through all of the suspension points. So this is the counterpart of the problem with futures, where you wouldn't find out where the bad value came from. With async await and our backtracer following stack frames like this, we're able to give you the entire logical, okay, this is why you have a bad value somewhere. And you can even drop into the debugger right away. So we will keep the process alive. You won't have to, oh no, now I have to reproduce the same with a debugger attached, right? So you can immediately drop in and debug. So to wrap up, I know I'm at time, so let's keep it quick. Swift really was able to address all of the issues that we stated at the beginning. We get memory safety, concurrency safety, and it's all in the existing code base. We do this, we focus on safety and ergonomics, but we don't sacrifice performance. And while I didn't talk about performance much here in this talk, as we migrated these important core actors in the FDB code base and used existing benchmarks that exercise them, we saw no regressions whatsoever. So if someone is using the excuse of, oh, we have to write C++ because performance, they might have to double check that assumption. And we really think Swift is a viable alternative here. One last thing I want to highlight is that it's not that, oh, we did this special thing for the FDB project. It's more that this is a strategic investment for C++ interop because we really want a successor language to replace C and C++. And the FDB project was just a great example to showcase all of that. And it's open source, so you can check it out, which is another great extra. Swift as a C++ successor. Yeah, we talked about that. Just checking if yeah, so the last thing I wanted to say, yeah. If you're considering or still using C++, please give Swift a look. And it's not just limited to being a C++ replacement. It's a totally viable just language on its own. So while we talked about C++ today, by itself, I hope the actor things and safety is probably very interesting for you all to check out. So thank you very much. And yeah, here's some links you can check out. Thank you.